In this video I am going to discuss about the synchronous machine. Synchronous machine means a motor or a generator. It is a doubly excited machine. It has two main parts, stator and a rotor. Mm, Stator carries a armature winding uh, mm, which operates with a three-phase AC supply, and a rotor carries field winding and it work on DC. When we talk about EMF induction, here also Lorentz principle is used, EMF is induced due to the relative motion between armature conductor and a field winding. Here in this case, armature winding is kept stationary and field flux is rotated for the EMF induction in armature conductor. When we talk about advantage of putting armature winding on the stator, these are the advantages. Uh, it is more economical and efficiency. More economical because here we use only 2 slip ring instead of 3 slip ring, and it's more economical because due to 2 slip ring I square R loss is less as compared to I square R loss of 3 slip ring. Okay, so it's more efficiency and better insulation. As we know that armature winding is a stationary winding, so we can put more and more insulation as per required. Efficient cooling, it is stationary, so cooling is also easy, and more output depend on the number of turns. As it is stationary, so we can put more and more turns because we don't have to rotate it, so we get more output. And convenient construction, as it is stationary part, so the maintenance part is also easy and construction is also easy. Synchronous speed, it is a conversion of electrical frequency in mechanical speed. Okay, this we can derive from here. We know that theta electrical equals to P by 2 theta mechanical. When we do derivation on both sides, then we obtained angular frequency equals to P by 2 angular speed. Okay, so when we make it more simplify, then 2 pi f equals to P by 2 2 pi n by 60, so we get n is equal to 120 f by p. So this is the synchronous speed, and ns, we also call it as ns, synchronous speed. And synchronous generator is preferred over induction generator because it fulfills the reactive power demand, and also for constant, and also it operates for constant frequency output. Okay, fixed frequency is required because sinusoidal of different frequency are orthogonal to each other, and hence they transfer zero net power. Y frequency are of 50 or 60 Hz. We take a frequency as a 50 or 60 Hz because due to some limitations, we know that overall efficiency of the power system depend on efficiency of boiler, turbine and alternator. Okay, among these, boiler has the minimum efficiency, turbine has the moderate, and alternator has the highest efficiency. When we talk about turbine, according to the mechanical point of view, turbine gives maximum efficiency at 3000 to 3600 rpm. Okay, so according to that, when we consider the minimum number of pole, that is 2, so we get by using the formula ns equals to 120 f by p, we get frequency as 50 or 60 Hz. In construction we have two main part. One is stator and rotor. Stator is same like stator of induction motor, which has three-phase distributed winding that work only on three-phase AC supply. Okay, when we talk about rotor, we have two types of rotor. One is salient pole rotor and another is cylindrical rotor. When we talk, basically what we have to remember in this, we have to remember the basically differences between them. And when we talk about equivalent circuit of salient pole rotor and cylindrical is different, we will study further. Now we will discuss only the difference, basic difference between the cylindrical and salient pole. When we talk about salient pole, it is a when we talk about salient pole rotor, and air gap is not uniform. Salient pole rotor is like this. Salient pole rotor is like this. Air gap, you can see air gap out here is very less, and here air gap is more. So in this way we say air gap is not uniform. And when we talk about cylindrical, the rotor part is throughout like this. It's a solid steel throughout. So there is a uniform air gap. So okay. So it is salient pole has a non-uniform air gap. So large centrifugal force can damage the rotor, so we run it at low speed, that is 50 to 1000 rpm only. So accordingly the pole will be from 120 to 6. Okay. So here we have uniform air gap, so less centrifugal force, so we can run it at high speed, that is 3000 to 1500 rpm. So accordingly the pole will be 2 to 4. Okay. And salient pole rotor is used in hydropower plant, and cylindrical rotor is used in steam turbine. Okay. Is also called turbo alternator, and salient pole rotor machine is also called hydral generator. Okay. And salient pole rotor, in salient pole rotor, rotor diameter is large, so stator will obviously be also be large, so we can put more conductor. We put more conductors, so we can get more output from it. Okay. When we talk about cylindrical rotor, its diameter is less but its axial length is large. Okay. And two more fact what we have to remember in this is that rotor is of solid steel made up of nickel molybdenum to increase the strength. Okay. And another fact we have to remember is 2 by 3rd of the rotor part is used for winding, and 1/3 is for used for pole formation, and 1/3 is used for pole formation. Okay. And when we talk about salient pole rotor, air gap is maximum along q axis, so reluctance is maximum. Air gap is minimum along d axis, so reluctance is minimum. Here you can say air gap is minimum along d axis. You can see d axis. Okay. And this one is q axis. Air gap is maximum. See, you can see maximum along q axis. Okay. So in this way we have to differentiate. And when we talk about this, we know very well it is an air gap is uniform, so we don't talk about that. Okay. And another difference is that it has a arc shape pole. Okay. Arc shape pole means like this this arc shape. This one is arc shape pole. Okay. Arc shape pole. See, arc shape pole. And another we have is chamfered pole. Chamfered pole means air gap is minimum at the center and it increases at the edge. And in arc shape pole, it is uniform air gap throughout the arc. Okay. This is the basic difference. So in arc shape pole, air gap is uniform. We saw flat top flux is formed due to flat top flux, flat top EMF. Flat top EMF means third harmonic present. Okay, so we make the pole chamfered. So we make the pole. So we use chamfered pole. In this we saw minimum air gap is at the center and air gap increases at the edge. Okay, in this way we get sinusoidal flux. Due to this construction we get sinusoidal flux, and if the sinusoidal flux, then we get sinusoidal EMF. That is our main motto to obtain. Okay, so in this we do like this. And when we talk about cylindrical rotor, we know that air gap is constant, so reluctance is constant throughout. Okay, so reluctance is constant throughout. So we cannot change the air gap to get the sinusoidal flux. So we cannot change the air gap to get sinusoidal flux. So what we do here is, to get sinusoidal flux, MMF must be varied sinusoidally. Okay, to get sinusoidal flux, MMF must be varied sinusoidally. So to do so, we have to change the number of turns across the rotor periphery. Okay, so where we have to change the number of turn, now we will decide that. Actually what we want maximum flux along D axis and minimum flux along Q axis. To get that condition, what we have to do, we have to do maximum turn along Q axis and minimum turn along D axis. Okay, we get approximate sinusoidal flux, and hence we get sinusoidal EMF. In working part, basically we discuss about the formation of EMF in the synchronous machine. Okay, so we start with basic 3 points. Slot angle beta, that is equals to 180 upon slot per pole, and slot per pole is also called pole pitch or phase sometime. Okay, and slot angle beta is phase displacement between two slots. Okay, and its formula is 180 upon slot per pole per phase. And we have phase band M, that is number of conductor belonging to number of conductor is in adjacent slot belonging to same phase group is the phase band represented by M, and its formula is slot per pole per phase. Okay, slot per pole per phase, or we can say pole pitch upon phase. Okay, and we have phase spread, that is angle acquired by phase band. Angle acquired by this thing, okay, is called phase spread. Angle acquired by phase band is represented as sigma, that is phase spread, and is m beta. Okay, when phase band m is integer, then we have full pitched and short pitch, both are possible. If m is integer, then full pitching and short pitching both are possible, and its distribution factor will be sin m beta by 2 upon m sin beta by 2. Okay, and when we get phase band, that is m in fraction, that is sk upon pk, then full pitching is not possible. Okay, only short pitching is possible, and its corresponding distribution factor will be sin m beta by 2 upon sk sin m beta by 2 sk. Okay, and one third type of distribution factor kd is when we have uniform distribution. In that case, like when we will find it is uniform distribution or not, if beta is very small, then we say that it is uniform distribution. Okay, and if it is uniform distribution, then we take kd as sin m beta by 2 upon beta m beta by 2. Okay. And we understood about the distribution factor. Now we have to remember about the pitching factor or pitching angle, short pitching angle. Okay, this is kp. Kp is cos epsilon by 2. That's all. And when we talk about winding factor, that is kp into kd. We understood about the kd. There are three type of kd. And we understood about the kp also. So we can find out what is winding factor. Okay. And another point what we have to remember is so in basically these point what we have to keep in mind is slot angle beta equals to 180 upon slot per pole, phase bend m equals to slot per pole per phase, sigma, and that is phase spread sigma is m beta, and corresponding when m is integer and when m is in fraction, so we have corresponding distribution factor. And third type of distribution factor is when uniform distribution, and kp and winding factor. Okay, these things we have to remember. And another part what we have to remember is when it is double layer winding, then number of slot equals to number of coil, and when it is single layer winding, then we have slot is equal to 2 into number of coil. Number of slot is equal to 2 into number of coil. Okay. And next we will discuss about the EMF equation. EMF equation is same as we studied in transformer and in three-phase induction motor. It's same like that. Okay. ERMS equals to 4.44 F and phi, and here only difference is phi is 2 BMDL by P. BM we know that flux density. Okay, we know BM flux density, and this one is D is represented diameter of stator, L is axial length of stator, P number of poles. Okay. This equation is like straight when it is full pitched and concentrated. Okay. When we talk about short pitching and concentrated, then we introduce a factor kp in the same formula. In the same formula we have to introduce kp, and we know kp is short pitching angle, and its formula is kp equals to cos epsilon by 2. See, ERMS equal to 4.44 F and phi m into kp. Only one factor is introduced when we do short pitching, that is cos epsilon by 2. Okay. So when we talk about short pitch plus distributed, okay, so here we have done short pitching and distribution both. Okay. For short pitching we will use kp factor. Okay. And for distributed we will use distribution factor. Okay. kp into kd, and we know kp into kd is kw, so we directly write kw. Okay. In the same formula we write 4.44 F and phi m into kw, that is kp into kd. Kp we understood what is kp, cos epsilon by 2, and kd we know kd is there are three types of kd. Okay. One is when we get phase bend, in integer and in fraction. Okay. When we get in integer we have kd equals to sin sigma by 2 upon m sin beta by 2, and when we have in fraction then we have sin m beta by 2 upon sk sin sigma by 2 sk. And another kd we have when it is when beta is very small, that is uniform distribution, we have sin m beta by 2 upon m beta by 2. Okay. We understood three type of kd we can use here. Okay. And next we have when we will do short pitching plus distribution plus to remove nth harmonic. Okay. If we do all these three things, then what we have to do is we have to use the same formula. Okay. Use the same formula. What we have to do is we will introduce n, multiplication of n in the factor of frequency, in the factor of pole frequency and all electrical angle. all electrical angle means sigma, beta and epsilon. Okay, wherever there is pole, frequency and all electrical angle, that is sigma, beta, epsilon, there we will multiply by n factor. Okay, this is the main thing what we have to remember in for nth order harmonic. So we can see clearly out here, we have is 4.44. Here we had frequencies, that's why we multiplied by n. Okay, and for phi m, and we know phi m is 2 bmdl by p, and here we had pole, that's why we multiplied by n. Okay, and kp we know cos epsilon by 2. Here we had electrical angle, that's why we multiplied by n. And here we had and for kd we know that sin m beta by 2 upon m sin beta by 2. Beta is electrical angle, that's why we multiplied by n. Okay, and okay, this is the main trick that we have to remember out here. And keep in mind that after doing these things, we have the advantage that copper saving is introduced, and but only disadvantage is that EMF is overall EMF is reduced, but its quality is good because it is harmonic free. That's why after doing this thing we get harmonic free, reduced EMF, and copper saving is also done. So to remove third harmonic by short pitching, put epsilon equals to 60 degree. To remove fifth harmonic by distributed winding, put sigma equals to 72 degree. Okay. When we talk about the types of armature winding, we have mainly concentrated, distributed, and short pitching and full pitching. Okay, concentrated, distributed, short pitching and full pitching. Concentrated we know very well, it's concentrated at the point. Okay, and short pitching we have short pitching and full pitching. And for distributed we have three types. Okay, for distributed we have three types, that's why we had three types of KD. Okay, one is for uniform distribution, another is for when m is that is phase band. When m we had integral slot winding, and we have fractional slot winding when m was in fraction and when m is in integer. Okay, these three type distribution factor we have already discussed out here. See here we have discussed three type of distribution factor. When m was integer, okay, we had this formula, and when m was in fraction we had this formula, and when we had beta very small, that is uniform distribution, we had this formula. Okay, torque production in synchronous machine. Torque is produced in both, whether it is generator or a motor. Okay, only difference is that produced torque in generator opposes the prime mover, and produced torque in motor supports the rotation of rotor. Okay, first we will discuss about the generator, how torque is produced in the generator. Okay, so when we talk about generator, we provide two types of input. One is we provide a mechanical input, and another is we provide the field excitation in the field winding. Okay, when we provide both the thing, rotor flux will continuously cut the stator conductor, that is armature winding. So EMF is induced in the stator winding. Okay, and as the load is connected in the stator winding, so armature current is formed, that is stator current. Armature current is formed. Due to this armature current, armature flux, that is stator flux is formed. Due to this stator flux, stator pole is formed, and the construction is done in such a way that stator pole is equal to the rotor pole. Okay, and both the stator and rotor pole are stationary with respect to each other with some angle. Okay. Due to this condition, stator pole is equal to rotor pole and they are stationary with respect to each other with some angle. A torque is developed, and this torque opposes the rotation of rotor, that is prime mover. Okay. And one more fact we have to remember is that rotor mmf always try to catch stator mmf. Okay. And when we talk about the phasor diagram of this synchronous generator, see, first of all, what we saw, first of all, field flux is given, and mechanical input is given. Field flux is given. Due to this field flux, induced emf is seen in the stator. Okay. Due to this field flux, induced emf is seen. Due to first field flux was formed, then induced emf. So according to that logic, we can say this induced emf lag field flux by 90. Okay. Induced emf lag field flux by 90. Due to this induced emf, as we have connected load in the across the stator winding, so armature current is there. Due to this armature current, armature flux is also there. Okay. And due to this armature flux is this and field flux is this, and when we combine both, we get resultant mmf. Okay. Resultant mmf is fr. Okay. And now when we talk about internal power factor angle, that is angle between induced emf and armature current, is internal power factor angle, denoted by psi. Okay. And delta is angle between field flux and armature field flux and resultant mmf. Field flux and resultant mmf, so this is delta. Okay. And angle between field flux and armature flux, that is lambda, that is also called torque angle. Okay. Lambda is also called torque angle, and that is 90 plus psi, and this delta is corresponding to power angle, torque angle, load angle. Okay. These all three things. In the same way, when we talk about the synchronous motor, working is similar to that. Okay. Working is similar to that. In case of synchronous motor, we provide two excitation. One is field and another is three-phase AC supply on the stator. Okay. Due to this, both these excitation, rotor and stator pole is formed. Rotor pole, and they are also constructed in such a way that rotor pole is equal to stator pole, and they are stationary with respect to each other with some angle. Due to this thing, torque is produced. Finally, what we have to remember in these two is that for the production of torque, whether in generator or a motor, the main requirement is stator pole should be equal to rotor pole, and they should be stationary with respect to each other with some angle. Okay. And in both the things we have same for the torque production. Okay. And rotor rotates, and after that, when the torque is developed, then rotor rotates in the direction of torque developed. Okay. Here also rotor flux tries to catch stator mmf. Okay. And when we talk about the phasor diagram, see, field flux come first, and after that emf is induced. And when we talk about a motor, current will be there, but that will be in opposite direction. Okay. So the armature flux is in opposite direction. See, opposite direction, and everything is same. Psi, delta and lambda is same. Angle between angle between induced emf and armature current is psi, and angle between field flux and resultant flux is delta. That is power angle, load angle, or torque angle. Okay. And angle between field flux and armature flux is lambda, that is 90 minus psi in case of motor. Okay. Next we will discuss about the equivalent circuit of a synchronous machine and phasor and vector diagram of a synchronous machine. Okay, when we talk about equivalent circuit of a synchronous generator and motor, these are the equivalent circuit. Here we have EMF, induced EMF, and reactance XS and resistance RA. Reactance XS is a XS consists of two parts. One is armature reactance and leakage reactance. Okay, in the same way here also we have this is back EMF, this is back EMF, and this is reactance. This is also armature reactance and leakage reactance and resistance. Okay, see you can easily get here we are getting current, okay, from the circuit diagram. So it is generator, and in here we are giving the current. Okay, so it is a motor. Okay, and remember one main point is that induced EMF always leads the terminal voltage by delta. Okay, induced EMF always leads the terminal voltage by delta, and in case of motor, induced EMF lags terminal voltage by delta. Okay, accordingly we can easily write the equation EF angle delta equals to Vt plus IaRa plus JIaXS. EF angle minus delta equals to Vt minus IaRa minus JIaXS. Okay, here we can easily write. So accordingly we can also write draw the phasor diagram. When we talk about phasor diagram, we take current as a reference. Okay, we take current as a reference. Here we can see that first we are considering for a lagging current. Okay, lagging current. When we consider a lagging current, in that case current will be lagging by the terminal voltage by phi. Okay, terminal voltage by phi. This is an external power factor angle. Phi is an external power factor angle, and psi. When we talk about psi means phi plus delta. Okay, phi means psi plus delta. Psi means phi plus delta. This is we have already discussed that psi is angle between EF and IA. Okay, that is induced EMF and armature current. Okay, see, this is the psi. Okay, that is internal power factor angle, and phi is external power factor angle. Okay, and this one is delta load angle, we already know. And when we talk about motor, psi we know that internal power factor angle, that is EF between EF and IA. So this is the psi, okay, and this one is the phi. VT and IA, angle between VT and IA is phi. Okay, so psi will be what? Phi minus delta psi, right? Psi is phi plus delta out here in generator. Okay, in case of motor we have this. Okay, and we know that in case of generator, induced EMF lead terminal voltage by delta. See, you can see induced EMF is this leading by terminal voltage by delta, and induced EMF this lagging by terminal voltage by delta. See, everything is satisfying out here. Okay, so accordingly we can write the equation. Okay, accordingly we can write the equation by using simply by Pythagoras theorem. You think like this. Okay, this is base perpendicular hypotenuse. EF square equals to this square plus this square, and this means what? This is Vt cos theta plus IaRa. Vt cos theta plus IaRa is this. Okay, this is square. And Vt sin theta plus IaXS, this is this. Okay, and accordingly we can get this angle is psi. Okay, tan psi equals to this upon this, tan psi equals this upon this, and psi we know very well what is psi. And accordingly for motor what we have to put is current. Just put current as negative. Okay, just put current as negative, and psi equals to phi minus delta. Okay, this change we have to do. Okay, these all we have studied for what? These all we have studied for what? For lagging current. Okay, And similarly, for leading current, just put angle as negative. Which angle? uh, mm, External power factor angle. Okay, just put external power factor angle as negative. Okay, see, here we have clearly written that suppose if you are given that 50 ampere 0.5 lag, in that case for generator you will take 50 ampere and angle should be positive. Okay, for case of lagging, angle will be positive 36.86, and for motor we know that current is in opposite direction, so negative sign. Okay, and angle will be positive. And in case of if it is 50 ampere and 0.5 lead, in that case, in case of generator, current will be positive and angle will be negative. In case of motor, we know current will become negative obviously, and angle will be negative. Okay, this is the difference. Okay, and one more thing we have to remember is that voltage drop for both motor and generator, Vt square plus EF square minus 2 Vt EF cos delta equals to IAX ZS. Okay, this is what is drop for both generator and motor. Okay, all above these equations are applied for per phase basis. Okay, and we know very well torque angle delta is angle between rotor mmf and rotor mmf and stator mmf, or induced mmf, or terminal voltage. Okay, and one more fact you have to remember is that with change in speed only frequency will change. Okay, and if need to remain constant, field flux need to maintain same to get rated current. Okay, field flux need to maintain same to get rated current. With change in speed, current will not increase or decrease, only frequency will increase or decrease. Okay, when we compare this phasor diagram from this to this previous one, okay, only difference is that say delta there is difference in delta. Okay, delta psi is same, psi is angle between EF and IA. Here also, there also angle between EF and IA. See, angle between EF and IA psi. In case of this one also, angle between EF and IA. Okay, EF and IA. Okay, so only difference is that there here delta is angle between Vt and EF, and there delta is angle between field flux and resultant flux. Okay, field flux and resultant, and there is no such external power factor angle, but here we have external power factor angle. Okay, this way we have to remember. When we talk about voltage drop in synchronous machine, we have three types of voltage drop. See, armature resistance drop, leakage drop, and armature reaction drop. Among these, armature reaction contributes the highest. Okay, so most of our question will be from armature reaction drop. Okay, this is the most important thing. Okay, and let's start from armature resistance drop. When we talk armature resistance drop, this is IA square RA drop. Okay, for star connection, RA equals to 2 RA equals to 2 RA, and for delta it is RA equals to 2 by 3 RA. And to have armature resistance drop, armature resistance drop we find out by using DC voltmeter and ammeter method. We know very well how to find resistance using voltmeter and ammeter method. So this is also called IA square RA drop. So in case of if it is star connected, then we get this RA is DC resistance. Okay, this overall RA equals to 2 RA, and this RA equals to 2 by 3 RA. Why we have done this? Okay, you can understand from here. See, in case of star, we have when we connect voltmeter and ammeter this way, then we get V equals to IARA. Okay, V equals to IARA plus IARA, because here we have two resistance connected. Okay, so therefore it will be 2 RA. Okay, and in the same way here also you can understand these things. Okay, these things you can understand why it is 3/2 RA. Okay. So whatever the resistance we have obtained out here is DC resistance. So we know that AC resistance is more than the DC resistance because due to skin effect. Okay, due to skin effect in AC, so it is RAC is equal to 1.5 RDC. Okay, and when we talk about leakage reactance, leakage resistance, it depends upon the air gap. Okay, leakage reactance, it depends upon the air gap. More the air gap, more will be the leakage reactance. Okay, more with the leakage reactance. Flux linking the stator only. If the flux is linking the stator only, then that is called leakage flux, represented by XAL. So EMF equals to IA XAL. When we talk about armature reaction, it is an interaction between field flux and armature flux. Okay, field flux and armature flux is called interaction between field flux and armature flux is called the armature reaction, and its nature depend on power factor and load. Okay, its nature depend on power factor and load. In case of generator and motor, we can see clearly for unity power factor, it is cross magnetization. For ZPF lag, for generator it is demagnetizing, and for motor it is magnetizing. For ZPF lead it is for generator magnetizing, and for this demagnetizing. And for lagging, cross magnetization plus demagnetization, cross magnetization plus magnetization. Leading, cross magnetization plus magnetization, cross magnetization plus demagnetization. How this occur? This is very easy to understand. See, let us consider for generator. Okay, when we consider for generator, suppose it is a unity power factor load. Okay, unity power factor load. Now come to this diagram. Okay, this is the phasor diagram of generator. Okay, this is the case of what? This is the case of what? This is the case of lagging power factor. See, lagging power factor. This is the case of lagging power factor. When we simplify this angle, we will get this angle. Okay, this angle and this angle. Okay, this angle will be for cross magnetization, and this will be for demagnetization. One flux is this way, one flux this way, so it will demagnetize this flux. Okay, so cross magnetization plus demagnetization for lagging. See, here we have cross magnetization plus demagnetization for lagging. If it is leading, if it is this way, leading means current will be here. Okay, here, so it will be demagnetization this way, and this will be cross magnetization. Okay, you can understand more clearly from here. Case of lagging. Okay, case of lagging power factor. See, the case of lagging power factor, this contributes the demagnetization for lagging, and this contributes the cross magnetization. Okay, and for leading, see, this will contribute the magnetization, and this will contribute the cross magnetization. And for unity, you can see clearly, and for unity, current will lie on this only. So only for unity, current will lie on this only. So it is cross magnetization only. Okay, so cross magnetization only. In the same way, we can find out for generator also. For motor also we can find out. See, for unity, we have this one. Okay, this one will contribute only for cross magnetization. When it comes for zero power factor lag, means this one, current will be this one. Okay, and its flux is opposite, you know very well, so it will be magnetization. Okay, in this way. See, for motor and generator both it is shown. Okay, and in the same way for leading, lagging power factor for motor and generator, you can see very well. It's very easy to understand. Okay, Voltage regulation in alternator. Voltage regulation basically means change in full load voltage with respect to no load voltage. Okay, and there are three type of voltage regulation: positive, zero, and negative. When full load terminal voltage is less than the no load terminal voltage, then it is called positive voltage regulation. When full load terminal voltage is equal to no load terminal voltage, then it is called zero voltage regulation. When full load terminal voltage is greater than the no load terminal voltage, then it is called negative voltage regulation. Okay, in voltage regulation basically we need to remember these three things. These three things: formula for voltage regulation: no load minus full load upon full load into 100. Okay, this is the formula for voltage regulation. And maximum voltage regulation is x into z pu. Okay, x into z per unit. And this maximum voltage regulation occur only when theta s equals to theta, where theta s is alternator impedance angle and theta is load impedance angle. We can say maximum voltage regulation occur only when alternator impedance angle is equal to load impedance angle. Okay, and zero voltage regulation, formula for zero voltage regulation is very important for gate exam. For zero voltage regulation means cos theta s plus theta equals to minus ia zs upon 2 vt. Okay, cos theta s plus theta equals to minus ia zs upon 2 vt. This is very important to remember, so remember this one. And next we need to understand the impedance significance of a voltage regulation. Why we need to know voltage regulation? What is the use of voltage regulation? That we need to understand. Okay, if there is more voltage regulation, then drop is more and power sharing will be less. If there is less voltage regulation, means less ZS, less drop, and power sharing will be more. Okay, the most important importance of voltage regulation is that it helps us to design automatic voltage regulator that work by regulating field current to increase EMF if terminal voltage is decreased. Okay, and to decrease EMF if terminal voltage is increased. Now when we talk about characteristic of alternator, we have total 6 type of characteristic. Okay, among these 4 type of characteristic is similar to DC, similar to DC generator characteristic. Okay, among this this open circuit characteristic is VT upon IF. Okay, VT upon IF, open circuit characteristic, except short circuit characteristic and ZPFC, all are same as in DC generator. Okay, except these two, all are same. Okay, so let's start from open circuit characteristic. Open circuit characteristic means this is the equivalent circuit of a alternator. Okay, and this is induced EMF, this is access, reactance, resistance part. Okay, and when we do not connect any load, then it is called open circuit characteristic. See, in this case, if we do not connect any load, then there is no IA. Okay, and there is no armature current, no armature reaction. Okay, if there is no armature reaction, then there is no decrement in field. Okay, then there is no decrement in field. When we keep on increasing, see, when field current is zero, still there is voltage VT, still there is some voltage. This is due to the residual flux. Okay, this is due to residual flux. Okay, when we keep on increasing the IF, then the terminal voltage will increase, and till till the IF is rated, it will increase, and after that it will become saturated. After that it will become saturated. Okay, this is the case. At low IF, at lower IF, see, at lower IF, phi is proportional to IF. As we increase field current, phi also increases. And at high IF, it become constant. Why? Because due to saturation part. Okay, this become constant. This we have to understand in this open circuit. When we talk about short circuit characteristic, it is characteristic between IA and IF. Okay, IA, that is short circuit current, and versus IF. Okay, open circuit was between VT and IF. Here it is IA and IF. Okay, IA and IF. See, this is a equivalent circuit. What we will do here is we will just short circuit this terminal. Okay, when we just short circuit this terminal, we generally neglect resistance, you know very well. We will consider only this one. And if we short circuit, then you only think only we have inductor. Okay, due to this inductor, what we will have, current will be lagging. Okay, armature current will be purely lagging. Okay, armature current is purely lagging. In case of purely lagging armature current in generator, we know very well that it will be armature reaction will be purely demagnetizing. Okay, armature reaction will be purely demagnetizing. If it is purely demagnetizing, then reduce field flux. It will reduce field flux, and machine will never get saturated. If we keep on increasing IF, IA will also increase, armature reaction will also increase. And if armature reaction will increase, then what will happen? Then phi will decrease. Okay, and machine will never get saturated. So it is linear in nature. So as a short circuit circuit characteristic is linear in nature. Okay, here we can say easily. Okay, when we talk about load characteristic, and ZPFC is the part of zero power factor characteristic, is the part of load characteristic only. Okay, zero power factor is a part of load characteristic, but zero power factor characteristic is this way. Okay, OCC we draw OCC, and ZPFC this one. Okay, when we draw these two, then we get zero power factor characteristic, that is between VT and IF. Load characteristic is also between VT and IF, and this is also between VT and IF. Okay, and in most of the exam these things are asked. Now what is the distance between this? This is IA and XS. Leakage reactance drop. This one is leakage reactance drop. Okay, these two, between these two difference is leakage reactance drop, and this one is minimum IF required to maintain IA. Okay, minimum IF required to maintain IA. Okay, and when we talk about load characteristic, this is between VT and IF at the rate at the IA and speed is constant. When IA and speed are constant, then VT versus IF is the load characteristic. Okay, and we know that load are of different type. Some are leading, lagging. Okay, when we have we know the equation of generator VT equals to EF minus JIAXS. Okay, when we have lagging load, suppose we have lagging load. Okay, then we will have this formula, and we know that for lagging load we have demagnetizing. Armature reaction is demagnetizing. We know very well, we have already studied why it is demagnetizing. Here also we can say lagging load, for lagging load we have demagnetizing armature reaction. Flux will decrease, so VT will decrease. Okay, VT decrease means what? Positive voltage regulation. We already know positive voltage regulation means full load terminal voltage is less than the no load terminal voltage. Okay, full load terminal voltage means full armature reaction. Armature reaction more means demagnetizing. Okay, demagnetizing means VT will decrease. Okay, VT will decrease, that's why it is positive voltage regulation. Okay, and when we talk about leading, ZPFC leading. Okay, then we have Vt equals to EF plus Ia excess. Okay. And armature reaction magnetizing in nature. Okay, if it is magnetizing in nature, then phi will increase and Vt will also increase, and we'll say it as negative voltage regulation. Here full load terminal voltage is greater than the no load terminal voltage. Okay, you must be wondering why this is minus out here and why it is plus out here in case of leading. Okay, we know that in case of lagging, we have current, whatever the current, angle minus 90. Okay, lagging means minus 90. Okay, and it is ZPFC, so minus 90. Okay, so minus 90 means what? Minus j. So minus j into minus j will be what? Minus plus, and j square will be minus. Okay, so ultimately we get minus Ia excess. And when we talk about this, we have Vt equals to EF plus Ia excess. Okay, why it came like this here? Okay, here it is ZPFC lead means Ia angle 90. Ia angle 90 means what? Plus j. Okay, Ia plus j. Okay, Ia plus j means what? Plus j into minus j will be what? You only think minus, and j square is minus plus. Okay, in this way. So now we have external characteristic. External characteristic means Vt versus Ia. With the condition that if and speed are maintained constant. Okay, if speed is maintained constant, then frequency will be constant. If if is maintained constant, then Ef will be constant. If frequency and If is constant, then Ef is also constant. Okay, external characteristic is Vt versus If, and when we connect different type of load means what? It will be leading, lagging, or unity power factor. Okay, unity power factor means resistance only, and lagging means inductor, and leading means capacitor. Okay, when we connect these three type of load, what will be the what will happen? These are done out here. Okay, when we connect inductor, that is lagging power factor load. Okay, when we connect lagging power factor load, current will be lagging. Okay, current will be obviously be lagging by terminal voltage and EV. Okay, and we know that in case of a generator, what we have, EF will be leading. EF will be induced voltage will be leading by delta. This one must be delta. Okay, induced voltage is leading by delta. Okay, induced voltage is leading terminal voltage by delta. Induced voltage is leading terminal voltage by delta. Okay, this is terminal voltage. Induced voltage is leading terminal voltage by delta. Okay, and here we have lagging current, so current is lagging. Okay, current is lagging. Okay, we can say, and we know in very well that we have already studied that now when we have lagging power factor means armature reaction will be demagnetizing, and armature reaction demagnetizing is positive voltage regulation. Okay, positive voltage regulation means phi will decrease, Vt will decrease, therefore Ef is greater than Vt. So okay, therefore Ef is greater than Vt. This we can easily understand. Okay, and in case of unity power factor, current will lie in the same phase. Okay, current will lie in the same phase as the terminal voltage. Okay, and armature reaction is cross magnetizing is positive voltage regulation only. Okay, if there is cross magnetization, it will flux will decrease only. Okay, that's why it is positive voltage regulation. Okay, so Vt will also increase, and if Vt increases, then Ef is greater than Vt. This is also the case of positive voltage regulation. Unity power factor means positive voltage regulation. Okay, remember that. And when we talk about armature reaction, when we talk for leading, see, current is leading by terminal voltage and Ef. Okay, so armature reaction is magnetizing out here, and armature reaction magnetizing, that is negative voltage regulation. Magnetizing means phi will increase, Vt will increase, therefore Vt is greater than Ef. Okay, so correspondingly we we understood these things all. Okay, these all things, and we know Vt equals to Ef minus Ia excess for lagging, and Vt equals to Ef plus Ia excess for leading. Okay, these two are the cases. Okay. So next what we have, Vt versus Ia. Vt versus Ia linear with negative slope, therefore curve decreases. Okay, Vt versus If negative okay, see, ZPFC lagging has negative slope, and ZPFC leading, Vt versus Ia linear slope with positive voltage. See, it is linear and positive voltage regulation. Okay, positive slope. Okay, curve is increasing, positive slope, curve is increasing, positive slope, curve is in positive zero power factor leading. Okay, for zero power factor lagging, curve is decreasing with negative slope, curve is decreasing with negative slope. Okay, in this way we have to draw the phasor characteristic. Okay, so this one is I rated, this one is I rated, and this one is ISC, EF upon XS. Okay, ISC. When we talk about compounding characteristic, it is between Ia versus If versus If at the rate Vt constant. Here we have to maintain Vt constant. Okay, so lagging power factor means armature reaction. Demagnetizing means positive voltage regulation, means phi will decrease, Vt will decrease. Okay, phi will decrease, Vt will decrease. To make Vt constant, what we have to increase, we have to increase the flux. Okay, to increase the flux, we have to increase the If. Okay, that is excitation or field current, we say. Okay, this is the sequence, to understand it very well. Okay, and we have Ia versus If, If versus Ia. Okay, see, ZPFC lead when we keep on decreasing, when we increase Ia, armature reaction will be demagnetizing, in case of lagging. For lagging, armature reaction demagnetizing, means phi will decrease, Vt will decrease. To make Vt constant, Ia phi is increased, to increase phi, If should increase. See, If is increasing. Okay, for leading, when we talk about for leading means magnetizing, armature reaction magnetizing means negative voltage regulation is this. Okay, negative voltage regulation is this, and negative voltage regulation means phi is increasing, Vt is increasing, phi is increasing, Vt. To make Vt constant, we have to decrease phi. To decrease phi, we have to decrease If. See, If is decreasing. Okay, with increase in Ia, If is decreasing. See, it is fully satisfying. Okay, this way we have to keep in mind. So finally, when we conclude, what are the characteristics we have in synchronous generator? Okay, we have open characteristic, we have open characteristic, that is similar to no load characteristic. Okay, of DC machine. Open characteristic, Vt versus If. Load characteristic, Vt versus If. And in open characteristic, Vt and Ef is same. Okay, so we can say Ef versus If or Vt versus If. Okay, but in case of load characteristic, Vt and Ef is different, so here we have to say only Vt versus If. Okay, load characteristic, and then we have external characteristic, Vt upon Ia, and next we have compounding characteristic, If upon Ia for Vt constant, and here we have speed and If and speed constant, and for load we have Ia and speed constant. Method to determine voltage regulation. Basically, there are 5 methods to determine the voltage regulation. One is direct method, that is directly by the formula, voltage regulation is equal to Ef minus Vt, no load minus full load upon full load. This is the most accurate method, but here we need to run the alternator at full load, so it become more costly. so we do not go for this method, so we go for alternate method to save energy. There are four other method. They are synchronous impedance method, also called EMF method, MMF method, and ZPF, that is also called Portier triangle method, and another is American Standard Association method. Okay, these are the methods to determine voltage regulation. So let's begin from synchronous impedance method. Synchronous impedance method does not give exact result because all drops are in EMF. Okay, and this is important method for get point of view, because most of the question is asked from this method. Okay, because this is important method because it introduces concept of synchronous impedance and synchronous reactance. It is a pessimistic method because we get voltage regulation more than the exact value. This happens because here we neglect the saturation, because here we neglect the effect of saturation. Okay, pessimistic method because we get voltage regulation more than the exact, and this happens because here we neglect the saturation of machine. Okay, that's why this happen. Next we come to MMF method. It is an optimistic method. This method also do not give you the exact result. It is an optimistic method that gives voltage regulation less than the actual value. All drops are taken in MMF. And ZPF, that is Portier triangle method. Here leakage taken as voltage drop, and armature is taken as MMF. Okay, hence it gives more accurate result than both above EMF and MMF method. The vertical distance between OCC and ZPFC gives total voltage drop across armature reaction and leakage. Okay, this one is more accurate than above two EMF and MMF method, because the main reason behind this is that here leakage is taken as voltage drop and armature reaction is taken as MMF. Okay, this is the main reason. And when we talk about American Standard Association method, American Standard Association method is this one. Okay, American Standard Association method, it considers saturation effect as a separate voltage drop. So it is most accurate method among all these four. This is the most accurate method. Okay, and voltage regulation in descending order. EMF has the highest voltage regulation. EMF, after that ASA, after Portier's, and then MMF. EMF, ASA, Portier's, MMF. In this way, this is the descending order. Okay. So most important method among these four are this one, synchronous impedance method. Okay, this one is mostly asked in exams. Okay. So how to find voltage regulation using this method? See, first of all we need to find in this method we need to find ZS. Main target is to find ZS. Okay, because RA we can easily find by using voltmeter and ammeter method. Okay, RA you can find easily by voltmeter and ammeter method. Okay, and after getting ZS we can find RA easily, and therefore you can get access by Pythagoras theorem. Okay, and after getting access you can easily get EF using this formula, Vt cos theta plus Ia RA whole square plus Vt sin theta plus Ia XS whole square and whole under root. Okay, and Fourth, we can use fourth step, you can directly use no load minus full load upon full load into 100. That is called voltage regulation. Okay, the main target is to find ZS. Okay, ZS we can find by two method. One is by this one. Okay, open circuit voltage upon short circuit current at the same IF. Mention this is the most important thing. Okay, IF should be same. An open circuit voltage and short circuit current at the same IF. Okay, is ZS. And from SCR also, if SCR is given, then we can also find directly the ZS. Okay, because SCR itself is 1 upon Z per unit. Okay, short circuit ratio, SCR is short circuit ratio. It is the SCR is basically the ratio of field current required to produce rated voltage. SCR is short circuit ratio. It is the ratio of field current required to produce rated voltage on open circuit to the field current required to produce rated current on short circuit. Okay, that is IF at the rate VOC rated, IF at the rate ISC rated, and also called 1 upon Z per unit. 1 upon Z per unit is also called Z base upon ZS, and it is also the ratio of ISC and I rated. Okay, ISC upon I rated is also SCR. This is the most important formula that we need to remember here. Okay, and also we need to know that there are two type of ZS. One is unsaturated ZS and one is another is saturated ZS. Unsaturated ZS is when for low field current. Okay, for low field current we get unsaturated ZS, that is higher. Okay, that is high and constant. Okay, unsaturated is high and constant, and saturated is at the rated field current and is comparatively lower value of ZS. Okay, comparatively lower value. From here you can understand the ZS. Okay, see, this is VT, okay, and this is IA, armature current. This is terminal voltage and this is field current. Okay, field current. This is OCC and SCC, open circuit current and short circuit current. Okay, see, from here you can this is the curve of ZS. Okay, see, for lower value of IF we have constant ZF. Okay, ZS we have constant ZS. This is unsaturated ZS. Okay, till here it is unsaturated. See, out here it is saturated and become constant. OCC become constant. Okay, OCC is getting constant. So this one is constant, but this one is still increasing. Okay, this current is still increasing. Okay, but voltage is getting constant. Voltage is getting constant, and it is still increasing for the higher value of IF. So overall ZSB is lower. So overall ZS is getting lower. See, you can see easily ZS is getting lower. Saturated, this is saturated, this is unsaturated. Okay, this one you need to keep in mind. This one is asked several times in exams. Okay, so okay. And one more point we need to keep in mind is this one, air gap. When we increase air gap, leakage will increase, reluctance will also increase. Okay, leakage will increase, reluctance will increase. Okay, if leakage increase, XAL will increase. Okay, if leakage increase, XAL will increase. But when reluctance will increase, armature flux will decrease. Armature flux will decrease means XAR will decrease, armature reactance will decrease. Okay, armature reactance will decrease, XAR decrease, armature reactance decrease. So XAR, we know that XAR is dominating in nature. So overall excess, we know that excess is combination of XAL and XAR, and here XAR is decreasing and XAR is dominating. So overall XAS will be decreasing. Okay, so we can say with increase in air gap, excess will decrease. Okay, that's why we'll say for with increase in air gap, excess will increase. If excess will increase, then what will happen? See, after that we need to keep in mind all these things. You need to remember, if excess is decreased, then ISC will increase, short circuit current will increase. Okay, and voltage drop will decrease. If excess decrease, voltage drop decrease. Voltage drop decrease means voltage regulation will decrease. If voltage regulation decrease, then power sharing will increase. Okay, and also with decrease in excess, stability will increase, and stability increase and SCR will increase. Stability and SCR will increase. Okay, with decrease in excess, stability and SCR will decrease. Okay, increase. Okay, this thing we need to keep in mind. In this voltage regulation, main points what we need to keep in mind is that this formula to find ZS. Okay, and SCR equals to IF at the rate VOC, IF at the rate ISC rated. Okay, 1 upon ZPU is equal to ISC upon I rated. Okay, these things you need to keep in mind, and these points we need to keep in mind. Okay, so these are all. Now let's study a power angle equation in alternator and motor. Okay, in power angle equation we study the dependency of power on power angle delta, and the equation is derived in such a way that armature current does not appear in the equation. Okay, when we talk about alternator, we know the equivalent circuit of alternator. Actually, power angle equation of alternator and motor is very easy. It just seems lengthy equations, but we can easily derive these equations in exams also. Like it's very easy. Let's understand how it is very easy. When we come to alternator, this is the equivalent circuit of a alternator. Okay, see, basically what we have to study is that in alternator and motor, in alternator we have to know output power, developed power, and for motor we have to know input power and developed power. Okay, that's all. These only 4 things we need to know. And power means active power and reactive power both. Okay, power means active power and reactive power both. So let's start with alternator. This is the equivalent circuit of alternator. When we talk about output power, see, current is coming out. Okay, output power means what? S out will be what? VI conjugate. Okay, VI conjugate, we already supposed that here current should not appear in the equation. Okay, so we'll remove this I. Okay, we can remove I by this minus this upon this, whatever the impedance is there. Okay, this thing we know very well. Okay, after simplifying all these conjugate and all, we finally get this thing. Okay, we finally get these things, and after this we can easily get P and Q, active power and reactive power. P means what? See, finally we have written in the short notes, directly we have written the P and Q. Okay, see, EF Vt by Zs cos theta s minus delta, and minus Vt square upon Zs cos theta s, and similarly we can put sign and get Q. Okay, Q out. Okay, similarly you can do that one. Okay, and after that, when we talk about developed power, S out means what? S out. Developed means what? Power is developed out here. Okay, induced EMF. Okay, developed power will be what? EF angle delta into I conjugate. EF angle delta into I conjugate. Okay, so developed power and I, we know the equation for I just put and simplify, we get this one. And similarly we can write the equations. Okay, similarly we can write the equation very easily. Okay, so this is what we need to keep in mind. You can easily derive these equations. And when we talk about when we actually mainly the equations that are used when RA is neglected. Okay, when RA is neglected, we don't have to do anything. We just have to put theta s equals to 90 degree in the same equations that we have obtained. Okay, just put theta s equals to 90 degree. Okay, just put theta s equals to 90 degree, so we can get easily these things. Okay, see, for the neglected, we already discussed that theta s equals to 90. Put theta s equals to 90. After putting this, you can easily match. Everything is matching out here. See, for s out, you can easily match by putting cos, you can get this, and by putting sine, you can get this. Okay, and for developed also, by putting cos, you can get this, by putting sine, you can get this one. Okay, see, everything is matching out here. And one thing we need to keep, one thing you can observe out here is that as we have already neglected RA, so there is no consumption of active power. See, both active power P out is equals to P developed, means there is no consumption of active power. And we have considered this reactance, so there is consumption of excess, so that's why it's not equal. See, developed will not equals to out. Developed will be always more than the out. Okay, because excess also absorbs some part of Q. Okay, this is the thing out here. Okay, and when we talk about stability limit, to improve stability of system, we need to increase P max limit. Okay, and that can be done by increasing induced EMF, that can be controlled by controlling IF, field current. Okay, by controlling field current, we can increase the induced EMF or decrease induced EMF, and that way we can increase the stability limits. Okay, and in the same way, we can derive the equations for motor also. See, this is the equivalent circuit of a motor, you can see. And here we know that here what we have to find out is S input power and developed power. Input power means what? VI conjugate, and I we know very well, VT minus IA upon impedance. Okay, this you can get after that. After simplifying, we get this after simplifying. And when we get to get active power and reactive power from this S, we know very well we have to put cos and sine. Cos for active power and sine for reactive power. See, this thing, everything will be matching out here. See, you can match out here, everything is matching. Okay, so in the same way, for developed power also, developed is out here. Okay, power developed is out here. Okay, power developed out here means EFIA conjugate. When we will simplify this and put sin theta and cos, sin and cos to get active power and reactive power. See, from here we have directly written. Okay, from here we have directly written. And when we will talk about after neglecting RA, we just here also we have to do the same. Just put theta s equals to 90 degree wherever there is theta s. Now put 90 degree. That's only the formula. Okay, final formula. And after this, we can put cos theta and sin theta to get active power and reactive power. After putting cos theta and sin theta, we are getting this thing. After putting cos theta and sin theta in these things, we are getting this. See, after putting cos theta, we get this one. Okay, see, after putting cos theta, we are getting this one. And for input power, we are getting this one. And for developed power, we are getting this one. Okay, see, everything is matching. Here also you can see we have neglected the RA. That's why active power is same, but we are considering excess. That's why there this is not equal. Reactive power is not equal because some part of Q is absorbed by excess. Okay, next important part that we need to remember is that stable operation of a alternator or a motor. That is, we can say stable operation of a synchronous machine. Okay, see, when when power angle delta, when power angle, that is delta, is less than the synchronous impedance angle, then power output is less than the maximum power. Okay, then this is the case of stable. Okay, when power angle is equal to the synchronous impedance angle, then output power is equal to the maximum power, that is marginally stable. When power angle delta is greater than the synchronous impedance angle, that is unstable case, that is the case of unstable. In both motor as well as alternator, this condition is applied for both motor as well as alternator. Okay, see, this thing you need to keep in mind, very important things. Okay, and when we talk about maximum output power with respect to delta in alternator and motor, both we have to know. Okay, maximum output power, when we talk about conditions for maximum output power, condition for maximum output power with respect to delta we can get from here. Okay, after doing the derivation with respect to delta, we get a condition that is power angle should be equal to synchronous impedance angle for both maximum output for alternator and alternator and motor. Both maximum output power condition is delta is equal to theta s. To get maximum output power, we just put this condition in this equation. You can directly get the equation. See, after putting this thing, this will become what, theta s minus theta s will be what, theta s minus theta s will be 0. Okay, so 0. See out here you can easily get this angle has become 0 and this one has remain as it is. And when we'll put in reactive power, this becomes 0, sine 0 is 0. That's why only this one is left, and reactive power is negative. Okay, reactive power is negative in case of alternator. So negative means is less than 0 means leading power factor, means alternator is operating at leading power factor. Alternator operating at leading power factor means giving leading current, means taking lagging current, means taking reactive power. Okay, and we know very well that we install a alternator and in order to take active power as well as reactive power both. But here at this maximum condition, at this maximum power output condition, we can see that machine is taking reactive power. So this cannot be used practically. So this is not practically feasible. So we do not do these things because machine is taking reactive power instead, but we need reactive power from the machine. Okay, at this condition alternator will take reactive power instead of giving. So this condition is practically not done. Okay, this condition not practically done. And when we talk about maximum power developed in alternator, value of delta at which maximum power developed lies beyond the stable range of angle delta, so it is not feasible. And maximum power developed in alternator is also not feasible because when we do this, the value of delta comes beyond the stable range of delta. That's why this is not also feasible. This is also not feasible. And next we will study about the maximum output power for maximum output power with respect to delta for motor. Okay, the power with respect to delta. See, this is the maximum. See, here also same thing. Impedance angle will equal to theta, will equal to power angle. Okay, so here also same thing we have. Okay, and we know that power output is directly proportional to the power developed. Okay, in motor, in case of motor, whatever the power developed, that only will get out. No, and that's why see, so power output means power developed. Okay, just put this condition out here. You can easily get P developed will be cos 90 minus cos and this one will become 0, therefore see 0 and this one, okay, and when this one will become 0 and this one remain, and this also working at leading power factor, okay. At maximum output power condition, motor and generator both are working at leading power factor, but in case of generator that is not practically used, okay, but this can be used practically, because in this case leading power factor means taking leading current means giving lagging current means giving reactive power at this maximum condition, and at this maximum output power condition of motor is giving reactive power, okay, giving reactive power. This is feasible, this we can practically use this thing, okay. When we talk about nature of reactive power, this is the most important topic, I think, because most of the questions are asked in gate and engineering service. See, most of the questions, so this is the most important topic that we need to keep in mind. It should be on the tip of tongue, okay. It's so important. Here we have discussed the under excited, normally excited, and over excited for generator as well as motor, okay. When we talk about under excited generator means IF is less, okay, IF field current is less. Under excited generator will absorb lagging VAR, okay. Absorbing lagging VAR means absorbing Q. Generator will absorb lagging VAR in case of under excited. Absorbing lagging VAR means delivering leading VAR, okay. Delivering leading VAR, so we say it is working at leading power factor, okay. So we can say that generator is working at leading power factor, so we can say generator working at leading power factor. And in this case, as it is giving, as it is absorbing reactive power, reactive power is less than 0, and EF cos delta is less than VT, okay. EF cos delta is less than VT. When we talk about when we do normally excitation, when we do normal, neither absorb nor deliver Q, okay, then it is called unity power factor, and Q out is 0. Q out is 0, and here Q out was negative, and here Q out is 0, and EF cos delta is VT. EF cos delta is equal to VT, okay. And when we talk about over excited, means more reactive power is present in the generator, and it will obviously deliver the reactive power. Delivering reactive power means generator is working at lagging power factor. Lagging power factor means Q out will be positive, and EF cos delta will be greater than VT, okay. EF cos delta will be greater than VT. Cos delta greater than VT. And when we talk in the same way, when we talk about motor at the under excited, motor deliver leading VAR and absorb lagging VAR, okay. Motor will deliver leading VAR and absorb lagging VAR, that is Q. So it is so its power factor is lagging, okay. Absorb lagging VAR, so its power factor is lagging, and Q in is greater than 0, and Q in is greater than 0, and EF cos delta is less than VT, and EF cos delta is less than VT. And for normally excited, neither absorb nor deliver, and Q in will be 0. And EF cos delta is equal to VT. And for over excited motor deliver lagging VAR but absorb leading VAR, so power factor is leading, okay. And Q in is negative, EF cos delta is greater than VT, okay. This thing you need to keep in mind, very important. Now let's study V curve and inverted V curve of generator and motor, okay. V curve is a curve of armature current versus field current at constant power, and an inverted V curve is a curve of power factor versus field current at constant power, okay, whether it is motor or a generator. Okay, let's discuss V curve for generator and motor. Okay, let's first discuss V curve for generator and motor. See, when IF is less, when field current is less for generator, when field current is less means under excited, when field current is more it is over excited, when it is between this then it is normally excited. We know very well, there is no confusion in this thing. Okay, and when it is under excited generator, for under excited generator, you only think for under excited generator what will be the power factor. For under excited means generator will take reactive power. It will take reactive power means it will take lagging current. It will take lagging current means it will give leading current. Giving leading current means we can say that generator is working at leading power factor. See, it is leading power factor. Generator is working at leading power factor. And similarly for over excited means generator will give reactive power means giving lagging current, so it is operating at lagging power factor. For over excited lagging power factor. Okay, and for normally excited peak, bottom peak will be the unity, that is normal excited. Okay, bottom peak will be the normal excited, that is unity. Okay, and when we talk about when we increase load, IA will increase. We know that very well. When we increase load, IA will increase, and V curve will shift towards upward. See, V curve is shifting towards upwards as power is increasing. That is, as load is increasing, V curve is shifting upward. In the same way, we can understand for motor also. V curve of motor and generator is same. Only difference is that for under excited motor, for under excited motor will take reactive power means take lagging current means it is operating at lagging. For under excited motor is operating at lagging. For over excited motor is working at leading, and for normally it is unity. For both same. Okay, and here also as load increase, IA will increase, and V curve will shift towards upward. See, V curve is shifting towards upward. Okay, so in the same way we can discuss for inverted V curve also. As we know, inverted V curve is a curve of power factor versus field current at constant power for both motor and generator. For generator, see, same thing we can repeat here. Okay, same thing for under excited and power factor we can repeat. Okay, under excited leading, okay, under excited leading, over excited lagging, and for normally excited it is unity. Okay, and for normally excited it is unity. Same like in motor we can do. Okay, under excited lagging, okay, under excited lagging, over excited leading, okay. So here and here also, as load increases, IA will increase. If IA increases, armature reaction will increase. If armature reaction increases, to compensate the armature reaction, field current will also increase for same power factor. An inverted V curve will shift towards right side. See, inverted V curve is shifting towards right side to fulfill the need of field current. Okay, to compensate armature reaction. See, okay, this is only we have to understand in V curve and inverted V curve. Parallel operation of alternator. There are many advantages of doing parallel operation of alternator. To meet large and changing demand, we need to do parallel operation of alternator. Cost of standby unit will be saved. Okay, and economy and utility is more. Okay, and necessary condition for parallel operation are phase sequence and terminal voltage of incoming alternator should be same as the infinite bus. Okay, and frequency of incoming alternator should be slightly higher than the existing, because after loading frequency will slightly decrease. and become equal to the infinite bus frequency. Okay, and synchronizing methods are dark lamp method and synchroscope method. When we talk about dark lamp method is this one. Okay, dark lamp method, first of all we need to do a setup. We'll connect a lamp between alternator and infinite bus of all three phases. Okay, and in between there will be switches. Okay, this after this connection we will observe the lamp. Okay, when lamps are never dark, it means that voltage magnitude is not equal. To make it equal, we will vary the field excitation of alternator. Okay, if a lamp flicker faster, means frequency difference between them is large. Okay, if lamp flicker slower, then frequency difference between alternator and bus is small. Okay, all lamp are dark simultaneously, means all lamp are getting dark at a time. Okay, it means that it has same phase sequence and magnitude. Okay, it means that alternator and bus is having same phase sequence and magnitude. Okay, if all lamp are dark in a sequence, that is if it is in a sequence A B C L A L B L C A B C, then generator frequency is greater than the bus frequency. And if it is in the sequence, if it is in opposite sequence A C B, then generator frequency is less than the bus frequency. And also remember that this is the condition of opposite phase sequence. Okay, if all lamp are dark in a sequence, then it is said to be opposite phase sequence. And you know very well, if it is in the ABC sequence, then okay, this thing you need to keep in mind. These two things we need to keep in mind out here: opposite phase sequence and generator frequency greater, generator frequency less than bus frequency. Okay, and only disadvantage of this method is that due to voltage across synchronizing switch give rise to synchronizing current. Okay, due to voltage across synchronizing give rise to synchronizing current. And second method of synchroscope method is that synchroscope method. Okay, synchroscope method looks like this. Okay, Okay, like when the pointer will rotate in clockwise direction, then we will conclude the generator frequency is greater than bus frequency. And when pointer will rotate in anti-clockwise direction, then we conclude that generator frequency is less than bus frequency. And rate of rotation of pointer says the difference between frequency. If the rate of rotation of pointer is faster, then frequency difference is more. If the rate of rotation of pointer is slower, then frequency difference is less. So ideally pointer should rotate in slowly in clockwise direction. Okay, that's all. Here we are studying the case of two alternator is in parallel. Okay, two alternator is in parallel, both have same magnitude, E1 equals to E2. Okay, we'll study both the condition at no load and at loaded condition. Okay, first let's study at no load. Okay, both the generator are in parallel and they are at no load. If we change the excitation, if we increase the excitation of generator 1, it means what? We are increasing IF, means we are giving reactive power to the generator 1. Okay, increasing IF means IF1 means what? Increasing IF1 means E1 generator 1 voltage will increase. Okay, if generator 1 voltage will increase, then there is voltage difference. Due to this voltage difference, E1 is greater than E2, and due to this voltage difference, ISY, that is synchronizing current, will flow. And the current will be E1 minus E2 upon their their impedances. Okay, so what will happen is that generator 1 will give reactive power to the generator 2. Okay, so E1 will decrease and E2 will increase, so finally they will become equal. In this way both the generator will get balanced. Okay, in this way both the generator will get balanced. Okay, what happen if we increase the if we increase the S1, that is active power is given to the generator 1. What happen if we increase the steam input to the generator 1? If we increase the steam input, then delta 1 will increase. If delta 1 will increase, then delta 1 greater than delta 2. Okay, and we know initially delta 1 was equal to delta 2, but here due to increase in delta 1, so delta 1 will be greater than delta 2. Therefore synchronizing current will flow. Due to this flow of synchronizing current, generator 1 will give active power to the generator 2. P1 will so delta 1 will decrease and delta 2 will increase, so finally delta 1 will become to delta 2. So finally delta 1 will become to delta 2. Okay, here it should be delta. Okay, here it should be delta 1. Okay, here it should be delta. Okay, delta 1 should be delta 2, so finally delta 1 will become to delta 2. In this way alternator will get balanced. Okay, when we talk about the case of loaded, when the generator are loaded, both the generator are in parallel and they are loaded, in that case, when if we change the excitation, if we increase the excitation of generator 1, machine with higher excitation will supply more reactive power, and machine with lower excitation will supply less reactive power. Okay, as we have increased the excitation of generator 1, then IA1 will increase and IA2 will decrease. P1 active power will remain same. Okay, and but reactive power of Q1 will increase and Q2 will decrease. So power factor of Q1 will power factor of Q1 will power factor of generator 1 will decrease and power factor of generator 2 will increase. Okay, and when we talk about change in steam input, when we increase the steam input of a machine generator 1, machine with higher steam input will supply more real power, and machine with lower steam input will supply less real power. Okay, and IA1 is more and IA2 is less, then P1 will be more and P2 will be less, but there is no change in reactive power. Q1 will is equal to Q2. So due to increase in P1, therefore power factor of generator 1 will increase and power factor of generator 2 will decrease. Okay, you can use the formula of power factor, how this become more and less. Okay, why this power factor is decreasing and why this power factor is increasing, and here why it is increasing, why it is decreasing. This you can understand by the logic of power factor is equal to P upon S. Okay, active power upon apparent power. Okay, active power upon apparent power. See, active power is same in both. Okay, active power is same in both, but here here apparent power is increasing due to increase in reactive power. Okay, if denominator is increasing, then what will happen? Power factor will decrease. Okay, power factor will decrease. So in the same way here also you can put the logic. In here reactive power is same, but power factor is P by S. Okay, if active power is increasing and S is S is in the denominator, then power factor will increase. Okay, and here it will decrease. So now we will study the alternator parallel to infinite bus. Now behavior of alternator when they are connected to a infinite bus bar. Okay, when it is loaded, when the alternators are loaded and connected in parallel to bus bar, if we vary the field excitation. If we vary the field excitation with steam input constant, if we vary the field excitation with steam input constant, then we will see the behavior of V curve. Okay, and we have already studied the V curve and inverted V curve. We can relate to that one. Okay, and when we increase the input, when we vary the steam input and with field current constant, then we will see the effect of inverted V curve. Okay, this is only the thing we need to keep in mind, and we can relate to V curve and inverted V curve as we have studied before. Okay, and when we talk about no load, when they are not loaded, okay, when they are not loaded but they are connected to the infinite bus, so what will happen? P 0 delta is 0. Okay, P 0 delta 0, because they are not loaded. Okay, so for under excited generator, ZPF lead, under excited means what? Under excited means it will take reactive power. Okay, it will take Q, means Q is negative. Okay, it will take reactive power, means it will give it will take lagging current, means give leading current, means ZPF lead. Okay, ZPF lead, and Q is negative. See this one you can understand from here. You know Q out for generator. Okay, you know the Q out formula for generator. This one is negative for ZPF lead. Okay, this one is negative for ZPF lead. See, this one whole less than 0. Okay, when we'll send this one this side, then we'll cancel this excess, and VT will also get cancelled. Then what will remain? EF cos delta is less than VT. Okay, this is what out here, EF cos delta less than VT. Okay, when it is normally excited means Q is 0. Okay, there is no flow of reactive power. Okay, there is no flow of reactive power, no current, so no current will flow from alternator to bus. Okay, no current will flow from alternator to bus. This is also a condition of floating condition. This is also a floating condition. See, Q is 0 means Q is equal to 0. This Q is equal to 0. When we will send it this side, cancel these things, we will get this one, E cos delta equals to V. And for over excited we have ZPF lag. We know very well why it is lag. Okay, and from here you can say Q will be positive. It will give reactive power, so Q will be positive. Q is positive means greater than 0, and we'll send this side. Okay, we'll cancel these things, we'll get this. Okay, that's all. Here we are briefly going to understand the swing equation. Okay, swing equation is m into d square del upon dt square equals to pm minus pe, where m is inertia constant, delta is angular displacement of an axis fixed to the rotor with respect to synchronously rotating axis. Delta is angular displacement of an axis fixed with rotor with respect to synchronously rotating axis. Okay, and PM is mechanical input and PE is electrical output. Okay, and this whole d square del upon dt square is acceleration, and this one is inertia. Okay, there are three cases. When PM equals to PE means input equals to output, means machine is at steady state. Okay, when input and output are equal, then there is neither acceleration nor deceleration. This acceleration part is 0. Okay, neither acceleration nor deceleration. When case 2, when PM is greater than PE, that is input is greater than output. When input is greater than output, then machine will accelerate. Okay, and d square del upon dt square will be greater than 0, and generator will accelerate. Okay, extra input, and whatever the input is given, it will go to the output, and extra input will become kinetic energy, and rotor speed will increase. Okay, and when in third case we have PM less than PE, means input is less than the output. when input is less than the output, then d square del upon dt square will be less than 0 and generator will decelerate. Extra power output is given from kinetic energy and rotor speed will decrease. Okay, and we need to understand this one because in ESC exam this has been asked many times. Okay, suppose we have a synchronous machine. Okay, suppose we have any synchronous machine. When it lie in this category, that is that synchronous machine is coupled and it is also given a field excitation. In that case, what will be that that machine will act as a alternator. Okay, and when it comes in this category, means it is decoupled and excitation is given. It is decoupled but excitation is given. It will work as motor if it is connected to infinite bus bar. Okay, if it is stator is connected to infinite bus bar, then it will work as motor. Okay, when it is coupled but excitation is equal to 0. Okay, then what will happen? If it is coupled and excitation is 0, if nr is greater, if speed is greater than the synchronous speed, and if its prime mover speed is greater than synchronous speed, then it will act as a induction generator. Okay, then it will act as induction generator. And when it is decoupled and excitation is also 0, decoupled and excitation also 0, decoupled and excitation also 0, and is connected to the infinite bus bar, then in case of cylindrical it will work as induction motor. In case of salient pole it will work as reluctance motor. Okay, so now we will study the droop characteristic. Okay, see here we have the droop characteristic. Okay, droop characteristic is the variation of field with respect to power is called droop characteristic. Okay, see now when the machine is at a steady state, means PM equals to PE. Okay, as we increase the load, means output will increase. Okay, output will increase and output is greater than input. Okay, P is greater than PM, and therefore d square del upon dt square will be less than 0, means machine will decelerate. Okay, means machine will decelerate means speed will decrease means frequency will decrease continuously. Generator loses synchronism. To prevent this, we use governing valve. Okay, to prevent this we use governing valve. See from here graph we can easily make out when power output is 0, in that case we have this frequency. As we are increasing the power output, then frequency starts decreasing. Okay, see at the full load power and full load power, and this frequency has fallen down to FL1. Okay, so when we talk about the formula, no load speed minus full load speed upon rated speed. Okay, and mostly rated speed is taken as full load frequency. Okay, mostly rated and no load frequency. This is in terms of speed. Okay, and this is in terms of frequency. Full load frequency minus no load frequency minus full load frequency upon F rated. F rated is usually taken as F no load. Okay, usually taken as F no load. Okay, if droop is from no load to full load, then we take F no load. Okay, if droop is from full load to no load, then we take full load frequency. Okay, and when we talk about load sharing based on droop characteristic, all alternator are in parallel. All alternator in parallel should give power of same frequency. Okay, all alternator in parallel should give same frequency, that is F. Okay, this thing you can understand from here. See, from this graph you can easily say this side graph is for generator 2 and this side is for generator 1. Okay, generator 1. okay. So we have the group characteristic, different group characteristic generator we have, but they are connected in parallel, so we have a common frequency, okay. And their power sharing is for generator 2, power sharing is P2, and it's for generator 2 no load frequency is this one, FNL2, and load frequency is FL2, okay. And full load power is PFL2, and the power sharing of generator 2 is P2, okay. Similarly, power sharing of generator 1 is P1, and its full load power is PFL1, and its full load no load frequency is FNL1, and load frequency is FL1, okay. So in this, how we make the formula, let's understand, okay. See, this triangle OAB is similar to triangle OCD, okay. This triangle and this triangle is similar, okay. When these two triangles are similar, we can write this thing, okay. If these two triangles are similar, we can write this, okay. If this OAB and OCD are similar, then we can write OA upon OC is equal to AB upon CD, okay. AB upon CD. Now you can find out what is OA and OC, AB and CD, okay. OA is what? FNL1 minus FNL minus F, okay. And this one is what? AB is what? AB is P1, okay. And CD is what? CD is PFL2, okay. This is what we have written. And when we get P1 equals to, by sending this one this side, then we get this for P1, and similarly we can get for P2 also. And when we get P1 and P2, we can find total power for delivered to the load. P load equals to P1 plus P2. See, finally we got this one. P1 equals to FNL1 minus F upon FNL1 minus FFL1 into PFL1. And similarly we have for P2, and for full load we can find this one, okay. Total power, okay. So losses and efficiency in alternator or synchronous machine, okay. There are total 4 type of losses. One is armature copper loss, field copper loss, rotational loss, and fourth is stray loss, okay. Armature copper loss we know very well, 3 into Ia square Ra, and field copper loss we know If square Rf, okay. And rotational copper loss we know core loss and mechanical loss. Core loss is hysteresis loss and eddy current loss, and mechanical loss is friction windage loss, okay. And stray loss is mostly neglected, okay. Consider only when it is given, okay. This one is neglected mostly, okay. To find these losses, we have following steps. In first step, what we have to do is just run the machine at rated speed without providing without connecting it into load, and without giving excitation, without connecting any load and without giving excitation, just rotate the machine, okay. Whatever the mechanical power input we are giving, that is friction windage loss, okay. What are the mechanical power we are giving? That is friction windage loss. And in second step, what we do is run the machine at rated speed without connecting any load, but give the field excitation. Then mechanical power input will be friction windage loss plus core loss also, okay. then we can get these two losses, and plus one more loss we have is DC source field winding loss, that is if square RF. Okay, these losses we will get after that. Okay, after connecting to field excitation. And in third step what we will do is in third step okay, when we talk about in third step what we will do is run the machine at rated speed at IA equals to ISC, and IF equals to IF rated field current rated field current is given, and IA is also full. Okay, ISC. Therefore whatever the mechanical input will be rotational loss, that is core loss plus friction windage loss, that is rotational loss, plus 3 IA square RA loss. Okay, this is also called short circuit loss. Okay, and plus DC source loss will be also there, IF square RF. Okay, these are the total losses. Okay, so short circuit loss is also called armature copper loss plus stray load loss. See, from here you can see how is the copper loss and stray load loss. Short circuit loss includes armature copper loss plus stray load loss. So RA effective will be short circuit loss upon 3 ISC square. Okay. So when we talk about power flow diagram of alternator and motor, see here we have the power flow diagram. Okay, okay. This we have alternator. For alternator we are giving input. See, for alternator what we give input, we give mechanical input plus field excitation. Okay, so this is the input. Okay, p mechanical plus field input, IF square RF. After giving these two input, what we first will see is rotational loss. Okay, rotational loss, that is friction windage loss plus core loss. Okay, friction windage loss plus core loss, and then whatever the power will be obtained, that is developed power, 3 EFIA cos psi. Okay, 3 EFIA, this psi is angle between EF and IA. Okay, internal power factor angle, we know very well. Okay, this is power developed, and whatever the power developed will be there, from there will be armature copper loss and stray load loss. Okay, this is also called short circuit loss. Okay, and after this whatever the power is obtained at a terminal, it will be 3 VT IA cos phi, that is external power factor angle phi. Okay, 3 VT square IA 3 VT IA cos phi. Okay, when we talk about efficiency is output upon input. What we have output, see, this is 3 VT IA cos phi, and output is this, and input we know very well, mechanical power, shaft power plus IF square RF into 100. Okay, this is the efficiency. When we talk about motor, and in motor what we give input. Okay, we know very well in motor what we give input, field excitation plus electrical input at stator, that is 3 VT IA cos phi, that is external power factor angle. Okay, external power factor angle phi, and after giving these two, what losses will be there, armature copper loss and stray load loss. Okay, after this we will get developed power. Okay, developed power is 3 EF IA cos psi is angle between EF and IA. Okay, after that we will get friction windage loss plus core loss, that is rotational loss. Okay, then finally we get shaft power. And efficiency, we know that output upon input, output is PSH and input is this one. Okay, these two is input, so we have written 3 VT IA cos phi plus IF square RF. Okay, into 100. So when we talk about maximum efficiency, we know very well for maximum efficiency, constant loss should be equal to variable loss. Okay, constant loss is what? Constant loss is rotational loss plus field plus field excitation loss. Okay, rotational loss is core loss plus friction windage loss plus if square rf if square rf loss equals to 3 ia square ra is variable loss. Okay, constant loss is rotational loss plus field excitation loss, and variable loss is 3 ia square ra, that is armature copper loss. Okay, these two should be equal for maximum efficiency. That's all in losses and efficiency. Till now whatever before whatever the equation that we have studied, that was for cylindrical. Okay, whatever the equation for ef 10 psi and whatever we have studied, no, equivalent circuit, that was for cylindrical. Now we will study for salient pole. Okay, for salient pole, it is also called two reaction theory. Okay, cylindrical had air gap constant, therefore armature reactance was constant, that is represented as xar. Okay, but in case of salient pole, air gap is not constant, so armature reactance is also not constant, it is represented as xaq and xad. Okay, xaq and xad, and when we add the leakage reactance xaq plus xal, it become xaq plus xl and xad plus xl. So finally we write it as xq and xd, and remember one thing, that xd is always greater than xq. Okay, and xd is direct axis synchronous reactance and xq is quadrature axis synchronous reactance. Okay, when we talk about the formulas, these are the formulas that we need to keep in mind. These are the formulas that we need to keep in mind. First of all, to find ef dash vt cos theta plus ia ra whole square plus vt sin theta plus ia xs. Before we had xs, but here we have xq. Okay, only difference is out here. Okay, only difference till here everything is same except this x. Replace xs by xq. Okay, till here everything is same as before only. Okay, so 10 psi equals to this and psi equals to delta plus phi. Okay, everything is same. Replace xs by xq, replace xs by xq. Okay, after that here we have two new things. Okay, two new formulas. Okay, so id equals to ia sin psi and iq equals to ia cos psi. Okay, id equals to ia sin psi, iq equals to ia cos psi. Therefore ef is equal to, overall ef is equal to ef dash plus id into xd minus xq, and when we talk about motor, we can use the same concept as previous. Current will become negative in the same formula, current will become negative, and psi is equal to phi minus delta, and for lagging we took positive theta. For lagging we took positive phi, and similarly for leading we will take negative. Okay, same concept is as previous one. Okay, as we studied in cylindrical wala equation. Okay, and when we talk about power angle equation for motor as well as generator is same. Okay, here we have a power angle equation. This is what we have to mug up only, and don't think how it came. Okay, power P equals to EF VT upon XS sine delta plus VT square upon 2 into 1 upon x q minus 1 upon xd into sine 2 delta. Okay, sine 2 delta. This one is electromagnetic power and this one is reluctance power. Okay, electromagnetic power, reluctance power. When we talk about torque, we know that P equals to omega t, therefore torque will be P upon omega. Here power should be like total power means what? This is per phase power. Okay, so its total power will be 3 into this. Okay, so this one is power, this one is 3 into EF VT by XS sine delta. This is electromagnetic torque. Okay, 3 into upon omega s. Okay, and for reluctance torque, 3 into VT square upon omega s 1 upon xt minus 1 upon xq into sine 2 delta upon omega s we have already done. Okay, this is reluctance torque, this is electromagnetic torque. Okay, so when we talk about determination of xd and xq, this is done by using slip test. Okay, this is done by using slip test, but here we are not studying too much about slip test. Okay, but remember the most important thing, that when ra is ignored and voltage and current are per phase, voltage and current are per phase. Okay, and when ra is ignored, then we write xd is equal to vmax upon I mean, and xq is equal to vmean upon I max. Okay, if series we know that xd is greater than xq. With that concept also we can make out that when we'll do Vmax upon I mean, then we'll get maximum, okay, value. So this is the logic to remember. Okay, if series reactance X is connected in the alternator, and then overall XD effective will be XD plus X, and XQ effective will be XQ plus X. Okay, that's all. Few points was left in determination of xd and xq, that is also known as slip test. Okay, and frequency in rotor equals to p n relative upon 120. Okay, and this we have already discussed. Okay, these points. And in slip test field excitation is constant and rotor is driven in such a way that speed is less than or more than the synchronous speed. Okay, this is only in the slip test we do. Okay, and next we will study about the synchronizing power and torque. Okay, synchronizing power and torque. Here we are going to study the synchronizing power and torque. Okay, the topic synchronizing power and torque is for both cylindrical type and salient pole type. Okay, for both. Okay, suppose we have either parallel alternators. Suppose we have either parallel alternators, or we have alternator connected to infinite bus bar. Okay, if we vary excitation or we vary steam. Okay, in either of the reason, synchronizing current, that is ISY, is produced. Okay, this synchronizing current will lead to the power and torque. Power associated to synchronizing current is called synchronizing power, and torque associated to the synchronizing current is torque. Okay, synchronizing torque. Okay, this TS and PS, that is synchronizing torque and synchronizing power, are transient nature. Okay, are transient nature and act as at the disturbance and bring back the system to original condition. Okay, this is basically this synchronizing power and synchronizing torque and is basically a transient in nature, and it will try to bring back the disturbed system to stable system. Okay, this is basically good for the system. Okay, this is wanted. Okay, it should be present in the system. Okay, synchronizing power coefficient. When we talk about synchronizing power coefficient, it is nothing, just it is the derivation with respect to delta. Okay, derivation of power with respect to delta. We know very well equation of power in cylindrical machine and salient pole machine. In cylindrical machine, we know P equals to EF Vt by XS sine delta, and for cylindrical we know EF Vt by XS sine delta plus Vt square upon 2 into 1 upon xd minus 1 upon xq minus 1 upon xt into sine 2 delta. Okay, this is the equation we know very well. And to find synchronizing power coefficient, basically synchronizing power coefficient is the rate at which power varies with respect to delta is called synchronizing power coefficient, also represented as PSY dp upon d del. Okay, when we do dp upon d del, after doing dp upon d del, we know it will be called as synchronizing power coefficient of cylindrical type, synchronizing power coefficient of salient type. Okay, after doing derivation, it will become EF for cylindrical type, EF Vt upon XS cos delta. It will be called as watt per electrical radian. When we can convert this into watt per mechanical degree by multiplying it by pi p by 360. How it become pi p by 360 from here? See, we know that theta electrical is to p by 2 theta mechanical. Okay, p by 2 into, and to convert radian to degree, to convert from radian to degree, we have done pi by 180. Okay, so it become pi p by 360 omega radian per degree. Okay, and after doing derivation of this thing, we can easily get EF Vt by xt cos delta Vt square 1 upon xt minus 1 upon xq cos 2 del. Okay, omega radian per. Okay, for total synchronizing power coefficient, multiply the power by 3, because these are per phase. Okay, so for total PSY we will multiply it by 3. Okay, overall over-excited machine are more rigidly coupled with other as compared to under-excited. Okay, so PSY is directly proportional to EF. Okay, we can say this. PSY also measures the stiffness and rigidity between coupling of stator and rotor. For stability, PSY should be greater than 0. Okay, these are the points that we need to keep in mind for synchronizing power coefficient. When we talk about synchronizing torque coefficient, it is nothing. We know the torque formula. Torque is equal to total power upon omega s. Omega s we know 2 pi ns by 60. Okay, and when we talk about synchronizing torque coefficient, we will just do derivation. We will just do the derivation of here we don't have to do derivation. We have already find out the synchronizing power coefficient. So from there we can easily, by dividing it by omega sm and multiplying it by 3, for to make it total power, we will multiply it by 3 and divide by omega sm to convert it into torque, and we can write it as by multiplying it by pi p by 360, we can say it as Newton meter per mechanical degree, and here also by multiplying it by pi p by 360, we can say it as Newton meter per mechanical degree. Okay, so finally what we have to study is Significance of synchronizing power. See, we have alternator. When we will vary the steam, what will happen? Delta will become delta plus del delta. Okay, so P becomes P dash. Okay, so synchronizing power PS equals to P dash minus P. P dash minus P. When we will do P dash minus P, we get synchronizing power into del. Okay. This is a power that bring back the disturbed machine to stable condition, that is at the ns. Okay, and when we talk about synchronizing torque, T is T dash minus T, that is TSY, synchronizing torque coefficient into del torque that bring back the system to a stable condition. Okay, in past trends of fast acting AVR and speed governor, delta is kept between 45 to 55 degree. Okay, now let's study hunting. Hunting topic is only in case of synchronous motor. Okay, hunting topic is only in case of synchronous motor. We will not study in synchronous generator. Okay, what is hunting? Rotor oscillation is seen rotor oscillation that is seen when VT is suddenly increased. Okay, terminal voltage suddenly increase, or field excitation is suddenly increase, or load is suddenly increase instead of gradual increment, or load content mechanical torque. This is called hunting. Okay, if either there are four reason. Okay, see, VT suddenly increase, IF suddenly increase, load suddenly increase, load content harmonic. Due to either of these reason, if there is oscillation in the rotor, then we say it as hunting. Okay, that's all. That is only the meaning of hunting in synchronous motor. Okay, effects of hunting are produce mechanical stress and fatigue in the shaft, surge in current and power factor, losses increases, temperature increases. To eliminate, what we can do? See, we can use flywheels, design machine with proper inertia, or we can use damper windings. See how damper winding help here. Everything is explained about damper windings. Okay, damper winding consists of low resistance, so that IF increase, full load torque will increase. And if full load torque increase, then but starting torque will decrease. Okay, but starting torque will decrease. It is made up of copper, brass, aluminum bars embedded in the slots of pole face of salient pole, but don't use in cylindrical rotor because its solid structure itself contain eddy current and damping exist there. Okay, projecting ends of bar are short circuited so that current can flow easily. There are two types of damper winding: incomplete type, complete type. Incomplete type, different pole are connected together. In incomplete type, different pole are connected together, and in incomplete, different pole are not connected together. Okay, and incomplete, they are connected together. That is also called emeritus circuit. Okay, how this damping winding work? Okay, when rotor speed is equal to synchronous speed, then there is no relative motion between stator RMF and damping bar, so no current flow and no EMF is developed, no torque is developed, so damping bar is inactive in this case. When speed of rotor is not equal to synchronous speed, then there is relative motion between stator RMF and damper bar, so EMF is induced and current flow. Torque is produced according to the Lenz's law. oppose the relative motion. Okay, it will oppose this torque will oppose the relative motion and try to bring back the rotor at synchronous speed, hence stability is achieved. Okay, this damper winding is also used in alternator to increase the stability. It also oppose a negative sequence component. Okay, so now at last we will study about the power factor correction. Okay, power factor correction. For power factor correction, see, keep this formula in mind: QSM equals to P1 tan phi 1 minus P2 tan phi 2. Okay, for power factor correction, over-excited synchronous machine motor is the most important. Over-excited synchronous motor is like a capacitor. Okay, over-excited synchronous motor is a load that operates at leading power factor, means it will take capacitive reactive power and it will give inductive reactive power to the supply, and we know that most of our load need inductive reactive power and give capacitive reactive power. So if we connect over-excited synchronous motor in parallel with our load, then reactive power demand is compensated and power factor is improved. Okay, starting of synchronous motor. TEM, electromagnetic torque, is directly proportional to armature flux into field flux sine omega s plus theta. Okay, when we talk about starting method of synchronous motor, there are three methods. One is auxiliary motor starting by damper winding and variable frequency starting. Okay, auxiliary method starting. Okay, first auxiliary method starting: rotate the synchronous motor with any other induction motor or DC motor near to NS, then give supply to the synchronous motor so that electromagnetic torque will rotate the motor at NS. And in damper winding method, it will start like an induction motor. Okay, due to relative motion between damper winding and stator RMF, synchronous motor will start like an induction motor. When it reaches near to NS, then electromagnetic torque will make a rotor to rotate at NS. And last we have frequency variable frequency starting. A rapid reversal of torque can be eliminated at the starting with low frequency. Okay, and gradually increase the frequency to rated required speed. Okay. Drawback of synchronous motor. We need DC excitation, starting, synchronizing and control device required. Okay, motor sensitive to system disturbances, and advantages are rotate at constant speed irrespective of variation of voltage. Okay, and it increase power factor. Size, weight, cost is less than induction motor for power rating 35 kilowatt to 2500 kilowatt. Okay, so that's all.